SQL at LinkedIn. So I'm Fangshi. I'm the staff software engineer here in the Spark team.
Get the mic with it.
Yeah, cool. So we will start by introducing the Spark SQL roadmap here, and then we will talk about the 4 projects we are working on, including the dataset improvements and the drawing algorithms, and also the plan level optimization like the W execution and the cost-based optimizations. So I'll start by talking about some basic Spark SQL adoptions here at LinkedIn. So in our clusters, 60% of jobs nowadays are running Spark jobs. And within all those Spark jobs, the majority, 2/3 of them are Spark SQL jobs, and the rest are RDD jobs. So because we have been actively promoting Spark SQL adoption at LinkedIn, so it has been a pretty good adoption rate, and most new jobs today are already using Spark SQL. And within all those Spark SQL jobs, we have seen about 2/3 of them are using data frame and SQL APIs, and 1/3 are using dataset APIs. So we find that the data frame API and SQL API are very popular in the general ETL pipelines, as well as the ad hoc and interactive use cases. And for dataset API, so we find it particularly popular among the AI engineer here because they are doing a lot of feature engineering work, and they need to write a lot of, they need a fine-grained control of their schemas doing a lot of their complex feature transformations. And it's the type-safe functionality of dataset API, and it is very suitable for those kind of use cases. That's why we find that the dataset API is actually very popular at LinkedIn, and we find the adoption is higher than the other companies have been talking with. So for the Spark SQL working group here at LinkedIn, and we have 2 goals. The first one is to enable computations that could not be easily completed before. So that we are really trying to push the scalability boundary of the SQL engine by supporting a very large and complex use cases. And also we are trying to make every Spark job here run faster. So the logistic here is that if we improve the engine, make every job run 1% faster, we can actually save millions of dollars here in our cluster. And to achieve these 2 goals, we are adopting a 3-level optimization strategies. So first is the operator level optimization. So we identify the most critical SQL operators, including the dataset 30 operators and drawing operators, and we're trying to make those operators better. And at the next level, we are trying to optimize the whole SQL plan, basically to make sure every job can have the best SQL plan. And the projects here, we include the adaptive execution and the cost-based optimization. And at an even higher level, what we are looking at is the cross-plan optimizations. So we haven't really been there yet, but the thing that we have been thinking about, including multi-query optimization, such as the automated cross-query or even cross-job caching, even some integration with the Dalivio and its materialization strategies. Okay, so next I will talk about the concrete project we have been working on here, including the 2 operator level optimization project and the 2 plan level optimization projects. So let's start with our dataset improvements. So as I said, the dataset API is actually pretty important here at LinkedIn. In a very simple code sample here, that we will using the Spark readers to create a data set of some tracking events, and then we'll perform a simple filter and a simple map operations there. So with this very simple code sample, actually in this physical plan there is several data transformation steps there. So after the table scan operator, and actually the data has to be converted from the Spark internal representation into the the domain object, the tracking event objects, and then it will get passed to the user lambda functions, and after that, the result will be converted back to the Spark internal representation. So even for these simple lambda functions, it has the kind of expensive data conversion overhead there, and we find that the performance issue will get even worse if your source data is ORC or Parquet, because there's no column pruning support in Dataset APIs, and the entire tracking event object has to be read from the disk into memory. But we really don't need that kind of we really don't need every column to be read into memory. And for RC and Parquet, for this simple code sample, if you use data frame API, which support native column pruning, and then we will find that the data set performance will be much worse. So I think this is a issue that the upstream is also aware of, and one of the community solution is in this year's Spark Summit talk, that Apple have a talk talking about their solution to improve the dataset performance. And in their solution, they are using a bytecode analyzer, and they are trying to convert the user lambda functions into the Spark native SQL expressions. So suppose user write s.id larger than 0. So with Apple's approach, they are trying to convert this lambda function into a native expression. Basically, in this way, when you write the dataset API, you will write dataset jobs, and you actually get performance similar or exactly the same as the data frame job. So what we find that at LinkedIn, there are a lot of very complex user lambda function in the feature engineering job, and it is very hard to understand the semantics of those user lambdas and convert into the data frame, the native APIs. So the solution that we are trying is using a bytecode analyzer, and we are trying to identify which column actually get accessed in those user lambda functions, and then we will prune out all those columns that are not needed. So in this simple code sample, that you actually only need 2 columns. And then with our solution, what we can do is we can push those 2 columns up to the readers, so that if the source data is ORC or Parquet, that only these 2 columns need to be read from disk. So using our approach, we find that we get a significant performance improvements as we migrate, our offline ecosystem is migrating from Emerald to ORC. But next, I want to talk about the drawing algorithm that we have been working on. So here is a recommendation use case at LinkedIn. So after some, the upstream feature engineering work, and we have 3 kinds of features here: the viewer features, and the entity feature, and the pair feature. The pair feature is the interactive feature between the viewer and entities. After you have these 3 kinds of features, simplified data pipeline, the machine learning pipeline, that we will join the pair feature with the viewer feature first, and then we get the intermediate result. We join with the entity feature. We are trying to perform this 3-way join to create the join record, the large join feature, and then we will pass the join feature into a machine learning model, a pre-trained machine learning model for scoring. After that, basically we can get rid of those all the features and just rank the scorables. And then finally, we find the goal is to produce the top n entities for each viewer. So in this simplified recommendation pipeline, we find that there is some data explosion problem. So the data shape is like a diamond. It means that after each join steps, the intermediate data gets exploded, but after the scoring phase, then the data gets shrinked. But we really don't need to materialize all those intermediate data because after the scoring they can be discarded. And the goal here that we have been working on is, can we create a join operator or join algorithm that can perform this three-way drawing and scoring in a single step without the need to explode the intermediate data. Because with this, when the data gets exploded, and it's very hard to complete, especially the second drawing. And what we find is that previously without our solutions, and those jobs is very hard to complete, even with the powerful Spark engine. So with our solution, we created a 2D partition drawing algorithm on Spark that can achieve this three-way drawing in a single step without exploding the data. So I'll quickly describe the algorithms. So first, we need to partition all the three types of input features, and we will partition the left table into n partitions. We will partition the left table into n partitions, and then we will partition the pair table into n times n partitions. So in this way, for every partition in the pair table, there's always a corresponding left partition and a corresponding right partition. So for each pair partition, we can join the left side with a sort merge drawing, and then we will join the right side with a shuffle hash drawing. And we are using this way because that's the most efficient way we find, and we don't need to with shuffle hash drawing that you have to cache some data to create a hash table in memory. But with our approach, that only need to cache the smaller side of the table. After that, for each joined record, we can just simply apply the scoring function right away, and then we will just in this stage we will just output the scorable. And then we will have another stage to just sort and rank the scorables. So in this way, all the three-way drawing and the scoring are completed in a single stage. So without solution, without our solution, the pipeline was taking more than 10 hours, and it's very unstable and failing all the time. With our solution, and such pipeline will get completed in 1 hour. So we talked about the two, the optimization we are doing at the Spark operator level. And next, I want to talk about the two plan level optimization that we have been working on. So adaptive execution. Adaptive execution is framework added into Spark that allow you to optimize the query plan while the job is running. So it is originally contributed by Intel, and then now it is being merged into Spark 3.0. And we have been using this solution early in our own Spark binaries. And what we find is that it has several major features, and one of the features that allow you to handle data skew in drawings. It's like probably the only viable skew drawing solution that we find in the upstream community. And this was actually pretty great in our internal system. And next, it provides a feature that allows you to convert a shuffle-based drawing to a broadcast drawing at runtime. And you need to perform the shuffle map stage first. It means that we'll write the shuffle file, and then it will look at the stats of those shuffle files and determine if the state one side of the table is small enough for a broadcast, and we'll convert the plan to a broadcast drawing. And what we find is that it's not, because you need to perform the first stage, the shuffle map stage first before it can convert to a broadcast drawing. So it actually not as efficient as if you perform the broadcast drawing from the beginning. So because of this, one thing that we have been thinking about is adaptive execution the right solution to optimize drawings? Because for drawings, always involve more than one stage. And adaptive execution is like you complete one stage and then you optimize based on the stats of this stage, and you optimize the next stage. Because it's like trying to perform a local optimization within one stage. But for drawings, sometimes you need a holistic view of the entire plan so that you can make better decisions. So as a result, we are trying, so we have been thinking about using other ways more than adaptive execution to optimize drawing. So the cost-based optimization is what we are working on right now. CBO is added into Spark in 2.3, and it allows you to optimize the query plan based on the operator cost. So at the query planning stage, you have operator DAG of the query plan, and with CBO, you actually get a cost DAG, and every operator in the query DAG has an associated cost, and this cost can be the data size or the number of records. And the benefit of CBO is that once you get this cost DAG, you can easily choose the best join strategy of each individual operators, such as choosing between a broadcast join, a shuffle hash join, or a sort merge join. And what's more, it can perform the multi-join reordering by choosing performing the simpler or less costly join first before performing the heavy joins. So, however, what we find is that the current CBO integrated into Spark has some usability issues. It's very hard to make it available here at LinkedIn. And the reason is that with CBO, it requires the input data, the input data set has very detailed stats like count, min, max, distinct, or even histograms. So basically, you have to pre-compute the stats for your input data before you can use CBO to optimize the query plan. So as a result, then we have to have scheduled workflows to compute stats for all the data set here at LinkedIn and all the time, because there will always be new data sets added. You have to keep adding, configuring the workflow to compute the stats, and even for the old data sets, we have new partitions added all the time. So that is a very expensive, workflow, and we find that it just become it's very hard for us to afford the cost. And I believe actually this is probably the one of the common so that CBO is hard to adopt at the wider Spark community. So to solve this problem, the approach that we are thinking about is, can we learn the stats from history? And the answer is yes, because the job runs all the time, and once the job reads the data, and it actually knows what the data stats should look like, or at least the portion of the stats that are really critical. So our goal here is that with a history-based approach, that we can eliminate the CBO's dependency on pre-compute stats on all the data sets. And we also want to make it a general approach so that this approach can benefit all SQL engines, not only to Spark, but also to other engines running in our system like Hive and Presto. So we have been using two approaches here. One is an instance-based learning approach, which means that one workflow can learn its detailed data stats from its previous runs, and we get some insights from a very classic paper called Leo, the DB2's learning optimizer. And we're also trying another approach, which is a model-based approach, which means that the workflow trying to get its required data sets from a generalized model. And we also get some insights from another paper called SageDB. So with our prototype, we actually find that our learning-based CBO have a very similar performance compared with the native CBO in Spark that require you to pre-compute stats. And both of this two CBO approach has better performance in for a lot of queries in the TCDS benchmarking. So because we see pretty promising results, and we plan to share more of our details with this learning-based CBO approach in the future talks. Okay, so that's the thing that I want to share today. And as a summary, today we talk about two operator level optimization we work on at linking here. This includes the dataset performance improvements and the drawing algorithms. And we also talk about our experience with two plan level optimization strategies, including the adaptive execution and the learning-based CBO.